In the previous recording, we discussed double slit interference. Actually, I'm going to add something to this, at least in terms of terminology. As you see from the title, we are calling it Young's double slit experiment, Young's double slit setup, and that's after Thomas Young, who devised this experiment for the first time. Just a quick review. The setup is based on having a source of monochromatic light. Remember, the meaning of monochromatic is that there is a single wavelength, a single color of light. So we have a monochromatic light source. What we do is we position a screen in front of that light source, and that's going to have two slits through it, two holes through it. Usually we have them as horizontal or vertical slits depending on the setup. Now, the purpose of the slits is that we can create through them two sources of coherent light. How does that happen? The light from the source, once it's going to reach the slits, if the slits are positioned at the same distance from the light source, when the light waves are going to arrive to each of the slits, they are going to be identical. Then, once the light is going to emerge from those slits, each of the slits is going to act as a light source by itself, and since the light coming into the slits is identical, the light coming out of each of the slits is going to be identical. It's going to be identical. What's more important, it's going to be coherent. The two light beams coming out of here are going to be in phase. Remember, the coherent means the phase relationship does not change. Now, in this case, the phase relationship is going to be zero. Now, what we discussed previously, these two light beams, once they meet at a point across from the slits and midway between the slits, both light beams are going to travel the same distance to get to that point. Since they are going to travel the same distance, by the time they are going to get there, they are going to still remain identical, meaning that they are going to be in phase, and they are going to add up constructively or interfere constructively. And we get bright light there, or bright interference, meaning constructive interference, meaning bright light. Now, as we move away from that middle point, the path traveled by the two light beams is not going to be the same anymore. There is going to be a point where the path difference between the two beams is going to be equal to lambda. When the path difference is going to be equal to lambda, we are still going to have constructive interference. Then we are going to have bright light. Again, when the path difference is going to be twice lambda, we are going to have constructive interference. When the path difference is 3 lambdas, we are going to again have two beams that are in phase, resulting in constructive interference. So we are going to have bright light whenever the path difference between the two light beams is going to be 0, lambda, 2 lambda, 3 lambda, 4 lambda, whatever integer multiple of the wavelength. And that's going to happen on top of this middle point and below it as well. It's going to happen for both cases. Now, there are points on the screen where the path difference between the beams is not going to be lambda. Okay, and one special case is when it's going to be lambda over 2. When it is going to be lambda over 2, then one wave have traveled a distance lambda over 2 more than the wave when they arrive at that point. Meaning the waves are going to be out of phase in this case instead of being in phase. Excuse me. If they are going to be out of phase, they are going to interfere destructively, resulting in no light. Okay, that's going to happen when the path difference is lambda over 2, or 3 lambda over 2, or 5 lambda over 2, or 7 lambda over 2, whatever odd integer multiple. We have here 1, 3, 5, 7, 9, whatever. Odd integer multiple of lambda over 2. Whenever we have an odd integer multiple of lambda over 2, we are going to have destructive interference. And again, that's going to happen on top of the middle point and below the middle point. Okay, how does this going to look like? Okay, here we have two pictures. One from this website. I encourage you to go to that website. You are going to see a lot of neat images and some explanations what's going on. But this is a computer-generated image. That's not a real-life image, but it illustrates the point. In this case, we have green light, the green wavelength. Now, if this is the middle point, this is where we have constructive interference, bright light. That would correspond to the middle point that we have in the previous screen, of a path difference of 0. Now, for a path difference of lambda, we are going to again have constructive interference. Twice lambda, again constructive interference. 3 lambda, we are going to have again constructive interference. And we are going to have it from both sides. So lambda here, twice lambda here, 3 lambda here, and so on. Okay. In the bottom setup here, we have more of a real-life setup. This is actually a picture from a real setup. These people here at Brown University have set it up for their lab handouts. Actually, in our lab handout, you have similar images, and when you are going to do the lab, you are going to see similar things. Okay, here, somewhere here, I'm not sure I'm identifying it, right? That's my central maximum, or the place where the path difference is 0. Okay, now it's difficult to decipher, but the next bright fringe is going to be here. That's going to correspond to lambda. This is the other one, lambda. Then twice lambda, 3 lambda, 4 lambda, 5 lambda, and in the other side as well. And then we have another place where we don't see something very well, and that's due to the diffraction. We'll talk about that at the end of this the end of this chapter. Now you see from the other side another one, and another one, and another one, and another one. The path difference, whenever you go from a bright fringe to another one, there is an increase of lambda in the path difference. Okay, we see the fringes here as well. Okay, here it is blocked because it's dark, we don't see much, but we see them wherever it's bright. Now, the places where we have destructive interference, we have no light. That's the dark fringe here in the computer-generated one. So the first one here is going to correspond to lambda over 2. The second one, 3 lambda over 2. Then 5 lambda over 2. Then 7 lambda over 2. And so on. We have the same order on the other side. Okay, here it's the same thing. Now they are more difficult to see, but in here between the two middle bright ones, we have a dark fringe. That's lambda over 2. And here is lambda, 3 lambda over 2, 5 lambda over 2, 7 lambda over 2, and so on. From the other side, we can look at it as well. Okay, now after this visual, in the next recording, we'll try to quantify these mathematically.